Hi everyone, Dave here again. We're going to start now on lecture 2. Let me just open it up. Here it is there. Full screen mode. Now, as I said in the previous lecture, at the beginning, the first slide of each lecture, I'll have a list of topics to cover, and as I said before, I won't read those to you. You guys can read yourselves. And again, just as a reminder, we'll have lecture objectives as well. Can I suggest what you do is just use them as a checklist, and after the lecture and after you've studied it, just go through and check to see you've picked up the main points. So I'll scroll through to those. Now, if you recall in the previous lecture, we'd touched on this idea that we could set out the elements in a table. The elements, of course, consisting of those particles of matter that contain a unique number of protons. So, as I pointed out in the previous lecture, something like helium has got 2 protons, an atomic number of 2, and every atom that is like that is, has the 2 protons, is indeed helium. Fluorine, it's 9, etc. I also pointed out to you that for every proton, there's 1 electron. So when you look at these atomic numbers here, these numbers correspond to not only the numbers of protons but numbers of electrons, and that's going to be important. Just to recap, I also pointed out to you that the elements are arranged in groups, and these groups have similar chemical properties, that is, they react the same, and that the periodic table is also laid out in periods, that is, rows, and each of these rows is numbered. So this top one here is number 1. Now let me just go to get a pen. So this row here, first row, number 1, consists only of 2 elements, hydrogen and helium. Second row consists of all of these here, etc. Next thing I want to point out to you is that the table's laid out in groups or clusters or blocks, however you wish to call it. The first block or cluster I want to look at are the metals. So you can see here that we've got the metals. This arrow here actually refers to everything to the left of this yellow group of elements. So if I just do that, so all of those elements there are metals, and leave metalloids for the moment. And the other group I just want to point out to you are the non-metals. There they are there, and they're everything to the right of that yellow cluster. Also, while I'm at it, we'll include hydrogen in here. Now, hydrogen's a bit of an odd element, and it's sometimes difficult to work out exactly where to place it, but it's definitely a non-metal, so in that sense it should actually sit over here. For other reasons, it could actually sit over here in this area, but for the moment we're going to group it in with the non-metals because that's indeed what it is. Alright, we should have a very quick look at the properties of metals. Now, everything I'm about to tell you is a generalization here. First of all, the metals are generally metallic grey or silver, and there's only a couple of exceptions for that, and that's copper and gold. They're good conductors of heat and electricity. They're malleable, that is, you can bend them and form them into many shapes, and they're ductile, that is, you can stretch them out. Most metals are solids. There's a few exceptions. Remember, I said all of these are generalizations. Exceptions being these 3 here, and this one here, you might know, this is actually mercury. They're generally of a high density, particularly in comparison to many of the non-metals. and they generally have a high melting point. And again, there's exceptions here. Obviously, these three here are actually liquids at room temperature and therefore don't have high melting points. What about the non-metals? Well, they tend to not have any luster, generally poor thermal conductors, that is, they can't conduct heat particularly well. They actually make good insulators. They're poor electrical conductors. The only exception to this is actually carbon in the form of graphite. Can't really go into the reason here why this is the case, but it is, as far as I know, the only exception. They can exist as solids, liquids and gases at room temperature, so quite a variation. Certainly nothing, certainly a lot more than what the metals are in terms of their physical states at room temperature. They tend to be brittle. That is, that you can try to bend them, but when you try to bend them, they actually break and crack. They're generally of a fairly low density in comparison to the metals, and they more often than not have a low melting point. But there are some exceptions again. I'm just giving you some generalizations here. Okay, I do want you to know a little bit about or remember some of the names of these groups. If you recall last time, I said that the groups themselves have got this fairly confusing numbering system depending on which country you're living in. So I will require you to remember the names of just a few groups. That's the first one there, the alkali metals, and obviously that's referring to all of the elements within this area in here. The next group name I want you to remember is this, the alkaline earths, and that belongs to this group here. This bunch of elements in here isn't a group, but it is a block. And this block in here, and I'll just draw a line here like this. This block here are the transition metals. They're sometimes referred to as the D block metals, and you'll see why a little bit later on. Two other groups I want you to remember the names of. One's the noble gases, very important, these elements over here, and the other one's the halogens, which is the group next to the noble gases. Now, I'm about to tell you the most important thing in chemistry, basically, and it's got to do with us working out the reasons why things react or are indeed stable. To do that, I just want you to look at this group over here, which is the noble gases. They're called noble because they're arrogant and they don't want to have anything to do with any other elements. In other words, they're very unreactive. Another way of putting that is that they're very stable, or, if you like, they're happy with their lot in life. Now, it just so happens with a whole bunch of experiments, the results came out which indicated very clearly that the reason why things react is to do with the electrons that they possess. So if you put the two ideas together, what you come up with is the fact that noble gases must have very stable electron configurations and numbers of electrons. So in other words, this noble gas here, helium, has 2 electrons, and that's a very stable state, having those 2 electrons. Neon's got 10 electrons, etc., etc. So what does all that mean? Well, if you're saying that all of these elements here, the noble gases, are very stable and happy, then the other elements aren't particularly stable and happy, and in fact they aspire to get the same number of electrons as the noble gases. So let's take an example. Let's look at fluorine. Fluorine's got 9 electrons, so it's right next to neon in the periodic table, and if it could somehow pick up 1 electron, it would then have 10 electrons, and it would have the same number as that very, very stable element neon. And that's in fact what happens. Fluorine's chemistry is dominated by reacting with other elements and trying to pick up an electron so that it ends up with 10 electrons instead of the 9 that it originally starts with. The other thing I'd just point out to you here is this fluorine atom could, I guess, as a strategy, rather than pick up 1 electron, lose 7 of them and look like helium. Out of those two alternatives, the easiest alternative is to just pick up the 1 electron, and that's obviously what it does. Now, if you look at the other elements underneath fluorine, then we have chlorine, etc. Chlorine is right next to argon in the periodic table, and you can see it's got 1 less electron, it's got 17, than argon. So its chemistry is dominated by picking up 1 electron and getting the same number of electrons as argon, in which case it's then stable and therefore quite unreactive. If we go over to this side of the periodic table with the alkali metals, we see a different thing going on. If we look at lithium here, it's got 3 electrons. Now, lithium could have really 2 strategies available to it. One would be to lose an electron, in which case it would look like helium, or its electrons at least, or it could pick up 7 and have an electron configuration like neon. So, the simplest one, of course, is to lose 1 electron, and that's in fact what it does. So lithium's chemistry is totally dominated by losing an electron to look like helium, or at least the electron configuration of lithium to look like helium. It's still lithium. What about sodium? Well, I think you can see the same strategy here. So sodium will tend to lose 1 electron to look like neon, potassium to look like argon, etc. So all of these metals here, the alkali metals, their chemistry is dominated by trying to lose 1 electron, and it's not surprising, therefore, that they actually sit in that group, and that group, of course, has very similar chemical properties. Alkaline earth metals now, you can see what's going on. Beryllium has 4 electrons. Its strategy is to lose 2 to look like helium. Magnesium's is to lose 2 to look like neon, etc. And you can now see why this periodic table is set out the way it is, with these things arranged in the groups as they are. There's a little summary for you explaining what I was just talking about, and a little bit more. So it's all there written down for you if you didn't quite pick up what I was talking about. So again, just to reiterate, elements in a group have similar chemistry. So all of these alkali metals have a similar chemistry, and they're aspiring in this case to look like the noble gases by losing 1 electron. All the halogens have a similar chemistry, and they're aspiring to gain 1 electron to look like the noble gases. Now, I think you can see from all that electrons are extremely important when we're thinking about chemistry. So we're going to look at the configuration of electrons in more detail, not only the numbers of electrons, but the way they're actually arranged. I'm going to leave that for the next part of the lecture. What?